Okay, hi everybody. So this is going to be take number 3. First take, I forgot to record. Second take, I got a call coming in which interrupts the Zoom and just cuts it off. So hopefully this lecture will actually be finished. Okay, so today this little lecture is going to talk about velocity and acceleration in 2 or 3 dimensions. And let's think of 3 dimensions because why not? You can always think of it 2D as 3D with 0 in the third component. So let's imagine that we have a particle that's moving with the position vector r of t. So you can think of you think of it as a little ball, it's moving. That's the ball is on the end of the vector r of t and moving around in space by the curve traced out by that function. Okay, so any position vector in space can be written as a position vector with a function, a one variable function of t in each of its components. Okay. And if you want to say what's the average velocity of that particle, well, you do like you did when you computed average velocity before. You look at the distance something travels. So this will be the distance basically along a straight line segment divided by how long it took you to do the traveling. Okay, so that's sort of a distance along a straight line. Okay, that's a way to compute the average velocity. And to get the instantaneous velocity, well, if that interval is getting smaller and smaller, that line segment is actually going towards, is getting more and more accurate for describing the curve. And so the instantaneous velocity is exactly what you get as you let delta t go to 0. And that's what we're going to call v of t. So instantaneous velocity, we really just call velocity usually. Okay. And now remembering what it means to take this limit, it means you're taking the limit in each of the component functions. But each of those guys is a Calc 1 limit. And you should recognize that as the definition of derivative. So v then turns out to be, the vector v turns out to be just the derivative of the position function exactly. In other words, a derivative in each component. Okay, so the velocity is just the derivative, the velocity is just the derivative of position. And that's exactly the way it was in Calc 1, except now we're in a vector format. Okay, so the next thing we want to talk about is what's the speed of that object. Okay, so the speed is going to be a scalar quantity, and you want it to be non-negative. So the speed is, and it turns out the only reasonable way to do that is to replace absolute value that you did in Calc 1 with the length of the vector v. Okay, so that's what we do. So that's the speed. It's the length of the velocity vector. And just like before, the acceleration is the rate of change of velocity. So a of t is just a derivative of v prime. I'm sorry, the derivative of v, which is the derivative of r prime, that is the second derivative of r. Okay. So let's take a simple example. Suppose we take up an object which is moving along a curve given by this vector. Okay. And notice, what is that curve? It almost looks like a helix, but this will be a helix going around the x-axis, opening around the x-axis, but it's not a circular helix because there's a different coefficient here. So this is cosine t. If this were just sine t, it would be a circular helix, opening very quickly because the x is increasing like t squared. Okay. But since that's a different coefficient, it's a ellipsoidal helix. And let's ask, what's the velocity vector for this particle? What's its speed and what's its acceleration? Okay, so to get the velocity, we just differentiate the position function. So if you can do derivatives, this is a kind of gimme question. It's 2ti minus sine tj plus 3 cosine tk. Okay. And now if you want to take the speed, that means you have to take the length of that vector. So we square each one of the components, add them up, and take the square root. So that'll be the square root of 4t squared plus sine squared plus 9 cosine squared. Okay. And if you want the acceleration, you just take the derivative of the velocity. So that will be 2i minus cosine tj minus 3 sine tk. And that's all there is to that one. Okay. So now let's try something that's a little bit different. Suppose I give you the acceleration. Suppose I tell you that the particle is moving with the acceleration vector, um, let's say ti plus e to the tj plus e to the minus tk. And suppose I also tell you that the velocity at time 0 is k, and that the position at time 0 is I minus, sorry, let me do j minus k. Okay. All right. And now I ask you to find the velocity and the position vectors. Okay. So how do we do this? Well, how did you do it in calculus? If you knew the acceleration, you integrated to get the velocity, because by the fundamental theorem of calculus, if you integrate the derivative, you get back the function. So to get v of t, I integrate v prime of t. Let me call it v prime of tau, d tau. And I'm going to integrate, well, let me do it that way. And then I get a plus c. Okay, I get a plus c. If I do it from 0 to t, then this will be exact. Okay. All right. So let's see what happens. So the derivative, though, I'm integrating. The derivative is the acceleration. So this is t times I plus e to the tj plus e to the minus tk. Running out of space. dt. Okay. All right. So let's see what happens when oops, I wrote t, these are taus. Can't use t in two places for different things. Those are all taus. So when I integrate tau d tau, what do I get? I get tau squared over 2 evaluated from t to 0, okay, times the vector I. And when I integrate e to the tau d tau, I get e to the tau, and I evaluate from t to 0 times the vector j. And when I integrate e to the minus tau d tau, that's hard to read, so that's e to the minus tau. When you integrate e to the minus tau, you'll get minus e to the minus tau from t to 0 times k. Okay, so let's see, that will be t squared over 2 minus 0 times I plus e to the t minus 1 times j plus e to the minus t, minus e to the minus t plus 1 times k. Okay. So that is v of t. And that is wrong. Okay, let's look at another example. And now I'm going to give you the acceleration, and an initial velocity and an initial position. So this should remind you of when you're given the acceleration in Calc 1 and then asked to find the initial position of the function. And then they can fancy it up with a few questions about, how high and stuff is it going to go. But basically, this is the idea. So what do you need to remember? You need to remember that the fundamental theorem of calculus says that if you integrate the derivative of the function, you get back the function up to a constant, except this is a vector, this is a vector. So the constant you're adding here better be a vector. So I'm going to think of this as a vector with constants C1, C2, and C3 in its components. Okay? And V prime is the acceleration. So this is going to be the integral of, and let me do it component-wise. Okay, so this is going to be the integral of T dt and then I'm going to have the integral of e to the t dt, and then I'm going to have the integral of e to the minus t dt, and then I get that arbitrary constant. Okay? So in other words, when you integrate t, you'll get t squared over 2 plus c1 as the first component. Here you'll get e to the t plus c2 as the second component, and then minus e to the minus 2, e to the minus t plus c3 as the third component. And there is your v of t, okay? Except we need those constants. But we're given an initial position. In other words, in this notation, v of 0 is 0, 0, 1. Okay? So what is v of 0 when we work it out here? From this one, v of 0, so this one's given. And when v of 0, when we work it out here, we get c1, 1 plus c2, minus 1 plus c3. Okay, so that tells me that c1 is 0. These two have to match. 1 plus c2 equals 0, so c2 is minus 1. And minus 1 plus c3 equals 0. I'm sorry, equals 1, so c3 equals 2. Because minus 1 plus c3 has to be equal to this one, which is 1. So that says that c3 equals 2. So v of t, if you want to go back to the ijk notation, will be t squared over 2 times I plus e to the t minus 1 times j plus minus e to the minus t plus 2 times k. Okay? All right, so easy enough on that one. Okay, now let's look at, pen bleeds through, so this becomes a little difficult. But now let's look at the kind of problem that I heard from lots of you that you worry about, a sort of word problem. So suppose I take a projectile and I fire it from ground level at an angle alpha. Okay, so the projectile gets fired at an angle alpha. Okay, with an initial velocity, which we will call v0. Okay, and that's constants in some direction, so we'll have to, so it has an x and a y component. And when that projectile is fired, it starts with that initial velocity. It's going to go, you can tell what, you know what it's going to do. It's going to go up for a while, and then it's going to come down, and then it's going to hit the ground. Okay, and this is the projectile is fired at an angle alpha from the horizon with initial velocity vector v0. Okay, and the only thing, and only gravity is working on it. Okay, so you don't need to know a ton of physics. Just physics that pretty much every, I don't know, maybe nowadays grade schooler, certainly high schooler knows, is that Newton's second law, which says that the force acting on that projectile is the mass times the acceleration. Okay, and what is the acceleration? And the only acceleration is due to gravity. We're going to neglect air resistance for right now. Okay, so the only thing that's working on it is gravity. And gravity works if you think of I as the x direction and j as the unit vector in the y direction, then gravity works in the direction minus the force due to gravity, rather, is minus mg times j, where g is the acceleration due to gravity. It's 9.8 if we're going to use meters per second squared. Okay. Okay. So what's the velocity then? So the acceleration is only due to gravity, and that is minus g times j. Okay, and that's the only thing that's working on that thing, on that projectile. So what's the velocity then? Then the velocity is going to be what you get when you integrate the acceleration. So that will give me minus gt times j plus a constant. Let me call it vector c1. Okay, because we're going to get two constants in this. Okay. But now what else do we know? We know that v at time 0 is vector v naught. On the other hand, when you evaluate this right-hand side at t equals 0, that says that's vector c1. So we have that the vector v of t, velocity vector v of t, is minus gt times j plus the initial velocity. Okay. Okay. And now, what about the initial position? Okay. So to get the initial position, we would have to integrate the velocity vector. Okay. So that will give me, that's the integral of minus gt j plus v0 dt. So r of t will be equal to minus gt squared over 2 times j plus v0t plus vector r of 0. It's not hard to see that that constant there would have to be the initial position, but it started from the ground. That's what I said. So r of 0 is equal to 0. So here's the formula for the position vector at time t. Okay. All right, fine. But now I'm going to ask, what are the parametric equations of the trajectory? In other words, I want to get in terms of the x component and the y component, okay? All right, so let's think about that for a minute. How can we express V0 in terms of what we're given in here? Okay, well, V0, it's set off with an initial velocity vector, but you're told what the initial velocity, the initial speed is. Okay, it's going up, so it's positive. So V0, the speed, is given. Okay. All right. And we know that the vector V0 from basic trigonometry, looking at my pitiful picture, which I can't fit in here. But basically, basic trigonometry says that the x component is going to be the length of the vector v0 time, I'm sorry, it's going to be v0, yeah, the length of the vector v0 times the cosine of alpha is the x component. And the y component is a similar thing with the sine. So this is the length of v0, which is, I'm calling little v0 with no vector above it, times the cosine of alpha, plus v0 times the sine of alpha. Okay, that's just basic trigonometry. Okay. So, oops, times the vector I, because this is in the I direction, and basically this is in the J direction. Okay. All righty, so that gives me a way to express R of t in terms of its I components and its J components. Because you see here we have R expressed, here's a J, but here we can't tell what's going in which direction. So let's do better than that. Okay, so what we have so far is, and I apologize, this paper is pretty bled through from the pen. Okay, so we now have R of t then is equal to minus G over 2t squared times J plus V0 cosine alpha t, maybe it's better to put the t in front, times I plus V0 sine alpha t times J. Okay. Okay. So there are the parametric equations of the trajectory. Okay, we can say, oh, well, I haven't written them yet, but the parametric equations of the trajectory are x is equal to g over 2t squared. X is in terms of this parameter. And y is, let me put this in a little better place, v0t cosine alpha minus cosine, sorry, this is the I direction is the x. So x is equal to v0t cosine alpha, and y is the j direction. That is the minus g over 2t squared plus v0t sine alpha. And here are your parametric equations. You have to look for x and y and the I and j directions. So that, sorry for the little botch up there, brain blip. Okay, so now let's ask another question. When does the object hit the ground? Well, let me phrase it differently. How far away from the initial point is the object when it hits the ground? Okay, so you can't see my picture up there before, but it goes up at some angle alpha. It goes up for a while, it comes down and hits the ground. Okay, so I'm asking you, what is this quantity d? What is this distance? When does it hit the ground? Okay, so it's going to hit the ground when? And what's an easily identifiable point for this? Well, notice that the y value is 0, both here and here. So it hits the ground when y equals 0. Okay, we just found the equation for y. So that says that y is equal to 0 if and only if g over 2t squared is equal to v0t sine alpha. Okay, So solving for t, we don't want to count the t equals 0 point. We knew that. We started from the ground level. So the other value for t that will work is when t is equal to v0 sine alpha multiplied by 2 divided by g. Okay. So that's when it hits the ground. Okay. So notice if we played with this a little bit better. Okay, so the d is the x distance when y equals 0. So d is x when y equals 0. But what is x? X is v0 t, and when y equals 0, t is 2 v0 sine alpha over g. So x is v0 t when x is 0 times cosine alpha. And so notice you can rewrite that using a little bit of trig, and if you like to make it look prettier, that's v0 sine 2 alpha over g. So that's the distance, how far away from the original spot the projectile hits the ground. Okay. So one final question on this. Suppose I ask you, at what angle is that distance maximized? So at what angle alpha is the distance traveled maximized? Is the distance traveled maximized? And let me move this paper from behind. It's a little distracting to see that. Okay, so remember, we worked out that the distance traveled is v0 squared sine 2 alpha divided by g. Okay, so when is that maximized? Well, when v0 is a constant, g is a constant, so the only thing that has a chance to slip around, you're asking at what angle is this maximized? That's when sine 2 alpha is maximized. Well, what's the biggest value that sine 2 alpha can ever have? It's 1. What angle gives you a sine of 1? That's the angle when the argument is equal to pi over 2. And so that says alpha is pi over 4. So in other words, when you shoot the particle up at a 45-degree angle, then the distance it's going to travel is maximized. Okay, so that's what this little problem shows you. Okay, so that's it for this little section.